So while that will be a very hard act to follow, I can make a very interesting segue, which is that I was at the SSC. It was my first permanent job, and I lived through the death of it, very painful death. So, actually, that was where I first met Stan. So I am going to talk about the Minos experiment. So we heard a little bit about it from Andre. I hope he hasn't stolen too many of my slides. Only I know that. Okay, so this is the kind of compulsory plan of the talk. But I think I've got lots of stuff in here. So I can talk about the scientific topic, but Andre's already done that. But I've got some history, which is really interesting. I've got politics, I've got money, I've got construction, I've got intrigue. Oh no, no intrigue. And then we go on to the experiment and the results. And I will also talk about some unexpected developments along the way, which I think kind of illustrate what you can do with an experiment once you build it, and which we might have seen if we had not made that decision about the apertures of the magnets also. But anyway, okay, so Andre went through all this, so I don't really have to do it again. Just though I would point out that while this unitary matrix that he talked about relates the weak eigenstates to the mass eigenstates, it does usefully factorize into the three kind of experimental regions. And this one here is the one that we mostly focused the Minos design on. And this one here, which is the reactors, is also something that we ended up having something to say about. And this final, the third matrix here, represents the solar mixing. So the mass eigenstates 1 and 2. And as Andre pointed out, we still don't know which one of the eigenstates is the heaviest, but we know what the difference in the mass squareds is. Okay, so going back to the previous talk, cast your mind back to 1991. And the SSC was actually being built at this time in Dallas. And LEP turned on in 1989, and LEP had measured the number of neutrinos, light neutrinos, to be 3. The radiative corrections industry had kind of really taken off, and they were starting to use those calculations to tease out new information from the Z mass and width, such as the top mass and the Higgs mass, potentially. And as you heard, the SSC was going to go after the Higgs. So, you know, many eyes, I would say the majority of eyes, were watching that kind of, that bit of physics unfold. But there were a small number of people who were paying attention to something different. And that was this atmospheric neutrino anomaly, which was ongoing back then. So this was a measurement that had been made by some proton decay experiments, and in particular, the ones, okay, just a minute. Okay, the ones in pink had more precise measurements. They had noticed that there were missing muon neutrinos. So as you see the cosmic ray shower kind of unfolding from an interaction in the atmosphere, you'd expect 2 muon neutrinos to 1 electron neutrino coming out of each pion. And what was seen, in fact, was that there were fewer muon neutrinos than were expected. So this picture is in black and white to remind you of how long ago it was. This one too. So this picture is particularly important because Kamiokande, then they took that measurement of the missing muon neutrinos and translated it into the oscillation parameters, assuming this simple 2-flavor oscillation probability. And so they were able to make a kind of estimate of the mixing angle and of the mass squared of the 2 mass eigenstates, difference of the 2 mass eigenstates. So this was kind of what everyone thought was the answer. the Japanese funding agency took it very seriously. So this is 1991, and they approved 100 million units of money to build the Super Kamiokande detector. Now, I should just point out here that that blue line is actually what the answer ended up being. So it wasn't quite right. Nevertheless, we in 1994, so 3 years after the Japanese had figured out that this was something to go after, I guess after the SSC closed, Fermilab called for expressions of interest for a long baseline neutrino oscillation experiment on the what was going to be called the NUMI neutrino beam. Now, there was already an experiment kind of planned for that called Cosmos, which was a short baseline experiment. And I'm afraid I don't know, but I should mention that the person who was running that experiment, who had proposed that experiment, was called Bill Ray. And I don't know exactly how important he was in the realization that Fermilab should start with a neutrino beam. But I suspect that he did have quite a lot to do with it, even though as the time went on and it seemed like there would not be any physics to find in a short baseline experiment, it was later cancelled. Anyway, there were three expressions of interest. So the one was from Barry Barish and Doug Michael, and the X-Macro collaboration. I think it was about 50 to 60 people. I can't remember. This is all from memory. That was a vacuum calorimeter type detector, and I think it was something like 15 kilotons. Then there was Maury Goodman and the Sudan 2 collaboration, also about 50 people, and they were also proposing a tracking calorimeter, but I think they were proposing something much smaller, like a kiloton. And then there was Stan. He sent in a one-page EOI, basically saying, "Oh, let's do it at SLAC. We can have a Cherenkov detector, and you know, the weather's better down there or something." Anyway, it turned out that this wouldn't have been such a bad idea, actually, beyond the fact that a Cherenkov detector would have had a lot more background, and that would have been a problem. But the distance, so these other two were calling for a baseline of about 700 kilometers, and Stan's was more like 1,300 kilometers, and actually that would have been quite good. But anyway, Minos was eventually kind of born out of the three efforts, and Stan was kind of brought in as the appointed by Fermilab leader to try and get the whole thing started. We had a competition for a name, and this is what Minos stood for: Main Injector Neutrino Oscillation Search, because yes, we didn't know they existed then for sure, so we were a search rather than a measurement. We got a great logo courtesy of Angela Gonzalez at Fermilab. This is our Fermilab, and this was our proposal cover. And you can see how like the picture of that Andre showed. This one's actually been used. This is the one. This is the one that was in my office. So
I got it from Million. Sorry.
Okay, so the idea was that the beam would point from Fermilab to the Sudan mine in Minnesota, 735 kilometers away through the earth. There was a huge contribution. I mean, this kind of the smashing together of all the people and getting the name, getting the ideas and everything. I mean, that took some time. And there was a contribution that shouldn't be forgotten from the University of Minnesota, who helped that to happen and helped to get the project started quickly, because as you know, these things take a long time to get go through proposals and approval and everything. And so they fronted the money to get the cavern ready. Also, the original 15 kiloton detector was eventually reduced to 5 kilotons. And I think that's something that always happens with neutrino experiments, is that you say, okay, you don't need as much mass as you said you wanted, because we'll make it up with the beam with more protons on target, except they never make it up with more protons on target. So it always takes longer. But anyway, and the total cost, I think, is about 50 million for the detector, 70 million for the beam. Again, by memory, so I don't know for sure the exact numbers. Now, we have a much better schematic of the NUMI beam, but I like this one because I wanted to show it because that's Stan's handwriting on there, and that's his first.
That's his handwriting.
That's his first, one of his slides explaining what happens, but basically the protons come in, and it's much like what happens in the atmosphere. The cosmic ray comes in, or the proton comes in, hits a target and makes pions, and then the pions decay to neutrinos, and then neutrinos go on to the first detector and then to Sudan, and everything else is kind of stopped in the rock. So the idea was to make a beam such that we could look at whether those muon neutrinos were really disappearing in a controlled way by starting with some muon neutrinos that we understood. So this is a very oft-used cartoon plot that Tricia made originally, hundreds of years ago, and this just demonstrates the simplistic idea of the two detector experiment. So you start with your unoscillated signal that's in your near detector, and the oscillated signal is what you measure in the far detector, and modulo knowing the normalizations that you expect due to the kinematics and the distance the beam, the second detector is away from the first. You can take the simple difference there, ratio there, and you see this characteristic shape here, which is evidence of oscillation, and that the distance of the dip, depth of the dip is related to the mixing angle, and the position of the dip is related to delta m squared. And that's really all there is to it. It's very simple, and it's always a good idea, in my experience, to start with a simple idea, not try and need a detector that's so complicated that it all unravels later when you find other errors, other differences that you hadn't thought of before. So then 1998 comes along and Super K gets their first result. And look, it's way down here. It's almost inconsistent with the Kamiokande result. And it somehow, I don't know whether it produced the need for the Balte review or whether the Balte review was going on anyway. But I was quite junior, and we had to have yet another review because it was argued that we shouldn't build Minos because it won't be able to reach all the way down here. Remember, we'd used that blue line as our estimate for of where we were going to be looking. So it was actually asserted in the review that we should be cancelled. And I remember that there were people from Super K in the review, on the review committee. So, and they were the ones who were arguing that we should be cancelled, pretty certain. And then I remember a particularly dark night when it was dark in both emotionally and because it was night. And I went to the user center at Fermilab during this review, and I was either with Jim Musser or with Carol. I can't remember who it was, but we came across Charlie sitting at the bar all by himself. And it was apparent to us that he was really serious. He was really seriously considering cancelling the project, which was, completely shocking. But luckily, the next day he came to his senses. Obviously, we'd had something to do with changing his mind. And groundbreaking day came up in 1999. And I find this picture, we've seen this picture a lot in the last couple of days. You can see Mike Witherall is hiding behind that mist. But and there's Stan looking particularly happy, as he should be on that day. But what I find the most interesting thing about this picture is that the only one of the people there who looks like they know how to wield the pickaxe is John O'Fallon. And everybody else looks like a complete amateur. So anyway, and here's Stan giving the address on that day to all the glitterati that are stuck in front of him there. So, as I said, construction. So no underground experiment should be without some pictures of men usually, but people doing really difficult stuff in inhospitable places. And here they are doing all this stuff, big excavation, very deep down, cold, miserable. And then they covered it all with concrete here and made a lovely cavern where you can see the first plane of the Minos detector getting ready to be put in. We were reviewed very often, and by Denny Lehman, as I understand it, he would, I think it was every 6 months, but it seemed like more often than that. And they reviewed both our detector and beam projects for ages before they discovered, or someone discovered, that the beam needed a whole redesign, and it was going to be 3 years delay. So I don't know what the review guys were doing really, but anyway, we had a 3-year delay on the delivery of the beam, but that didn't stop us with the detector, which was finished on time and on budget. But I'll come back to that. But in between time, another unforeseen event happened where art came to the Sudan mine. So this, I don't know if any of you have been, or I'm sure lots of you have been to see this artistic installation on the wall of the cavern, but it's really amazing. You can stand across and look at this, and it's on an incredibly uneven surface. When you look at it from the distance, it looks completely flat, and it's got all kinds of famous scientists pictured in it, and planets, and symbols and everything. It's art, and it's very nice. So as I said, on time, on budget, but the beam was late. So we were ready taking cosmic rays though in 2003, and here's our bar detector, 5.4 kilotons, and this is the near detector. And now, talking about the gold standard, the key thing here is that the two detectors were functionally identical. So they had magnetic fields, they're made of steel, and so you see this spaghetti look coming out of the front there. That's the coil, and the near detector is this weird shape because we wanted to ensure that the magnetic field in the region where we were going to be measuring the neutrinos was exactly the same as the magnetic field in the big detector far away. So the technology that we used was steel planes, 1 inch thick, and then 4 centimeter wide scintillator strips with wavelength shifting fiber in them to capture the particles that came out from the neutrinos interaction in the ion, all read out by multi-anode photomultipliers. Okay, and then we ran up until 2013, and then we ran in the higher energy configuration after the NOVA experiment came online in a configuration we called Minos Plus, which I will talk about. But I would also mention right here, as I'm mentioning NOVA, that my understanding is that Stan was pivotal in the original design of the NOVA experiment. And I remember him with his white Mac laptop working on writing in C, I guess, or C++, some simulations for the NOVA experiment and what the detector should look like way back in the day. I thought it was a bit premature of him really, but I didn't say anything. And anyway, it wasn't, obviously. He was always a visionary thinker. So here was our final data. So you can see on the left, this is the reconstructed energy of our neutrinos in the far detector. We took the pink ones in the low energy regime and the blue ones in the medium energy regime. And you can see in brown what the distribution would look like if there were no oscillations. We take the aforementioned ratio, and you see the characteristic shape for sure. And we measured that in terms of the parameters of delta m squared and sine squared theta 2,3. And I think, yes, here are all our various measurements. So along the bottom is always the mixing angle. The top row is sine squared 2 theta 2,3, and on the bottom we were able to use a 3-flavor analysis to get sine squared theta 2,3, and up the side it's delta m squared. And so you can see that in 2006, you can see the super K measurements there looking very precise compared to ours in 2006. Then 2008, you can see where the black lines are us. Over here in 2011, we're really doing very well, very precise measurement of delta M squared. And then in 2013, this was our last, the last measurement from the low energy data. And then nowadays you see pictures that look more like this because we're looking at the angle within the free flavor paradigm. And this was our last measurement, including the Minos plus data, where we've split up the beam measurement compared to the atmospheric measurement, which we also did measuring the neutrinos from the atmosphere. So I think the point, apart from pointing out as time went on, we did better and better in terms of our measurement, I would point out that Minos really dominated the neutrino oscillation parameter measurements for about 6 or 7 years. And all the neutrino conferences, we were the ones who had the best measurements and new measurements of the mixing parameters up until about 2012. Okay, so I said I'd talk about unforeseen developments. This is the second one. And this was very unforeseen for me, that the Minos near detector building would be the best looking building on the Fermilab site. And, you know, it was amazing. I don't know who designed it and how it happened, but I remember showing up there. We had our first reception or something there and thinking, wow, we're at Fermilab. Anyway, yes, so scientifically, the unforeseen development that I'm going to talk about just now is looking for electron neutrino appearance. So the experiment was designed to look for muon neutrino disappearance. So we had big, thick 1-inch thick planes of steel. The muons would be easily visible as they went through the steel. And we didn't think too much about trying to find electrons. But the subdominant appearance of electron neutrinos suddenly became, as soon as it was confirmed that the muon neutrinos were disappearing, we had to immediately start thinking about, okay, well, can we see the electrons? And Stan, this is a thing that I found, it just happened to be on my desk recently, but it was from 1998, and it was Stan laying out how we could go about looking for electron neutrinos in our detector. Eventually, we used a precursor to machine learning, really, to tease out that signal, a massive library of Monte Carlo events. And we called that the library event matching method, which increased our efficiency. So here's our final result. Just about the same time as T to K, their first measurement, you can see Minos on the left and T to K on the right. The top plot is the 90% confidence level, the 90% confidence level on the top, 68% confidence level on the bottom for T to K, and Minos is the blue and red. So you can see blue is 68 and red is 90. The line down there, so Diabay came online in 2012 as well, and they made a very definitive measurement of this angle, θ13. And so the real uncertainty left on this plot was mixing angle θ23 down there. And so when you take that into account, you see this band here, which is our best guess, best estimate of this quantity now. And you can see that we were actually spot on, and T to K was a little lucky. They were able to get a bigger effect, really, because their central value was further away from 0. But anyway, this was our most reference paper. Okay, so more unforeseen developments. 2011. So we didn't really expect there to be a fire in the mine shaft, and the detector got covered in soap suds, which turned out to be also unexpected, because look at it now, after they cleaned it up, it had never looked so clean. Sparkling and shining, and all ready for action. And the mine crew did an absolutely exceptional job in recovering from that potential catastrophe. So another one in 2011 was that it was reported in the New York Times that neutrinos go faster than the speed of light. And this was a
5 minutes.
This was a measurement by the opera experiment. Anyway, we were encouraged by Pierre Badoni. We had money. We were showered in money, basically. Never before had it happened, to remake our old measurement of the speed of neutrinos, which we'd done before. And we eventually did do that. And we found that indeed the neutrinos are traveling at the speed of light with 1 part in 10 to the -6. So our measurements, while not particularly unexpected, is the best existing measurement of real neutrino velocity, and not the velocity from the protons to the neutrinos, actually neutrinos to neutrinos. Yes, so scientifically though, the other thing I think that we achieved with the Minos experiment, especially with Minos Plus, was an extended reach looking for sterile neutrinos, which have been in the news for, a lot recently. But we have, I don't think I really have time to properly explain this, but basically, if you draw our experiment in terms of L/E, we have the near detector here and the far detector here. The point is that if you've got neutrinos disappearing, so that's that's what you would see if you had sterile neutrinos, they would just not be there in the far detector. But you would have to see them disappearing in the near detector too. And so you need to make sure that both detectors are completely synchronized, really, to get a very good measurement of where the wiggle room is for a sterile neutrino. And it turns out with our experiment, using a covariance matrix to constrain that, there's almost nowhere for the sterile neutrino to hide. And actually you can see that in this plot, that the Minos measurement was the green one, and then the Minos Plus measurement improved that enormously by an order of magnitude in both directions. Yes, and then we were able to combine our results with Diabet and Bougie and turn the mixing angle 1,4 into or 2,4 into sine squared, so we could put it on the plot with all the other experiments. So we did very well, I think, with the sterile neutrinos. Well, finally, no neutrino experiment would be complete without a cross-section measurement, and we did our bit there too. You can see, you can't really see, but our points are in here holding their own in a particular area, and that's our points are the red ones on that was the result from our paper. Okay, so winding up, some numbers that are interesting. We had at the peak about 250 collaborators. It took us 10 years from writing the proposal to getting the beam, 11 years to collect the data. We got through 8 targets, 4 horns, 4 Fermilab directors, 5 co-spokespeople, and we produced 42 papers. And this is these are our best. The first 3 are our best referenced ones. I told you the electron neutrino one got 910 citations. This was our first new mu disappearance paper, and this was the one in 2008. And our search for sterile neutrinos, much more recent, here, has nearly 200. So, as I said, our peak number of collaborators was about in 2008, I think. But this is a snapshot of all the people on that paper who did not have academic jobs when that paper was written and who do now. So that's 42 individuals, all of whom, I think, got a letter from Stan that helped them get their job. So thank you.
Questions for Can I make a funny comment? About the superluminal neutrinos. This might have been appreciated by people who don't read Italian newspapers, but there was a Minister of Public Education who congratulated the team for shipping those neutrinos in the underground tunnel from Gran Sasso,
Yeah, I remember.
from CERN to Gran Sasso. Now, the minister doesn't know that the neutrinos flow through the earth is excusable, but the minister doesn't know that probably the entire Italian economy would not be sufficient to drill a hole. CERN to Gran Sasso. That is kind of more serious.
I'll ask a question. What was the impact of your early years at SSC and what happened on your future career? Can you unpack that? It's a pretty traumatic experience to
Yeah,
go
it
through.
was actually very traumatic.
Yeah.
Yeah, I mean, but well, I had to go and get another job and start on something else, So that's what I did. But I guess the thing that I took away from it though is skepticism about big projects getting funded in this country.
Probably inappropriate.
So anyone who talks to me knows what I'm thinking about the next one, and I'm afraid. But probably it'll all be fine.
Yes.
It's actually on the same vein, and the answer might be potentially scary, but I think we've just heard two stories of. I love I love the frequency with which, for example, the word integrity came up, and we see brilliant ideas that are going to produce great science being put out there, and some either horror stories or nearly horror stories in how the politics and the real world aspects of it actually work. What lessons have we, and what lessons are the most important that you think we haven't learned as a field? In that,
I think we just carry on making the same mistakes over and over again. If you're really asking me my personal opinion.
I mean, we
we just get bigger committees to make more bland decisions.
Yeah.
The bigger, the less likely you are to get anything that's going to be particularly visionary, and that's what we do. So I don't know.
I'll just say, I think one thing I heard my dad say a lot was just that we don't have enough elected officials with a science background. And that really caused a misunderstanding of a lot of the big projects that were needed. And I don't know what the current votes were, but at the time he had stats like, 90+% had law degrees and 2% had science degrees. So, it was something like that. And so, that clearly needs to change if we're going to depend upon government funding going forward.
2% is an overestimate.
Okay, yeah, maybe it's 1%.
They're mostly
0.1.
doctors.
0.1%.
They're mostly doctors. Doctors have a science.
You mean that's how
Yeah,
the
that's how you
science is
get the
categorized? That's not even,
Yeah.
yeah.
That is a true statement. I'm not making, they're mostly doctors, a medical. That's right.
and one Bill Foster.
And one physics physicist.
Yeah.
Who is not here.
We could make sure that the lawyers had some technical competence.
That's a big stretch.
Other comments on this or any other?
No.
Right, so I think so first let's thank the speaker again.